He is from Birmingham, Alabama. He holds a BS from the University of Alabama and a PhD from the University of North Carolina, Chapel Hill. He studies how, and I translated this from what you gave me, again, doing my extension job. He studies how marine organisms move in larger ocean systems to better inform conservation and management efforts. He currently works for the University of Miami at the Physical Oceanography Division of NOAA's Atlantic Oceanographic and Meteorological Laboratory. He has published more than 37 scientific articles, which have accrued more than 1,000 citations. Approximately 20% of his published work is on the chemstrally sea turtle, an animal he has never seen in the wild. It's terrible, I know, it's sad. So, please, Dr. Putman, join us.
Thank you. So, thank you for that very warm welcome and introduction. Today I'll be talking about modeling abundance and sources of oceanic stage sea turtles impacted by the Deepwater Horizon oil spill. And here's an outline of my talk. So modeling, you're going to hear a lot about modeling today from a number of the speakers. So I'll give you some perspectives on modeling. Then I'll go into a generalized description of the sea turtle life cycle, where I'll highlight the importance of the oceanic juvenile stage. And then I'll explain how I go about modeling turtle movement and distribution of that stage, and how that gets applied to understanding impacts of the Deepwater Horizon oil spill on turtles. And the things I'll be focusing on are not necessarily how many turtles are sick or whatever, but the sort of putting this in a context of, what's sort of the geographic scope of impacts? What are the populations impacted? What are the numbers of turtles in that area at that time? And what are the likely origins of those turtles? And I'll close with some conclusions from all of this. So when you think about modeling, often something like this comes to mind. It's complicated. You have a lot of inputs that feed into some quantitative mathematical equation or two that give you outputs that then hopefully give you information to understand things, larger scale processes that you wouldn't otherwise have information on. And so certainly this is what I do, and this is one of the ways that I think about it. So taking disparate information and making it into some sort of cohesive story. And this isn't a great thing to look at first thing in the morning. So I'd like to give a perspective on this that's perhaps a bit more digestible. So the art of modeling. There are different ways that you can go about modeling, and it's sort of like different ways of going about creating art. So in this case, this is a Jacques-Louis David painting. It's impressive in scope. It's 10 meters across. It's in the Louvre, and it took him and his students 2 years to produce. This is showing the coronation of Josephine and Napoleon, and this is like a really detailed hindcast kind of model of something, of an event that occurred in the past, and it's you can look at and ask questions about how does the Pope feel about this, how does Napoleon's mother feel about this, what's going on in these sorts of situations. Now, of course, just because it's detailed and intricate and looks very realistic doesn't mean it's all true. Like Napoleon's mother wasn't there. She was miffed at him. He and his brothers had an argument. But over time, in a couple of years when this was being produced, she was happy with Napoleon. Everything had worked out amicably. And it's appropriate for her to sort of be placed in that setting because she's happy that he made himself emperor. Now, you might see some sort of models like this today from perhaps Benny Galloway. Details, intricate, but then you might throw in this TED multiplier to make it all work and smooth things over. Models don't have to be intricate to be useful, right? So you can have an approach where you are intentionally stepping away from the details and saying, what are the basic processes going on that define an ecological function or that kind of thing. And you might see something like this from Charles Caillouet, where we're intentionally trying to simplify the question and identify what is the key thing that's driving a process. Myself might be more along the lines of this Marcel Duchamp painting, where you have what was a very nice painting, but is now sort of cheap and mass-produced to the extent that it's boring. And what I would do is, put a couple of pieces of additional pinning on it, give it a provocative title that is funny if you read it aloud in French, and provide a new way of looking at a process, a new way of using a model for slightly different purposes that gives you a new way of thinking about an old problem. And we'll be talking about these models in the context of sea turtle life history and oil spills and the like. And it's good to keep in mind that when the models you see, sort of fall somewhere in the spectrum, and they're useful for different purposes, and each one has its sort of own place. But you want to know the type of model you're looking at so you can interpret it and know what it is that you should be taking home from it. So we'll jump into a description of a generalized sea turtle life cycle. So the sea turtles are fascinating animals. Their life cycle is characterized by movement. And what you see here is a depiction of the distribution of North Atlantic loggerheads, their life cycle placed out on a map. And this is generally characteristic of most other populations and species, where you have sea turtles nesting on sandy beaches, relatively restricted area of their range. The juveniles scramble off the beach as they hatch and migrate offshore, where they are carried by ocean current systems across, in some cases, entire ocean basins. As they age over the subsequent years, they'll return to near-shore waters and set up foraging grounds. As they become mature, the females and the adults return to their nesting, their natal sites, or their natal regions, to reproduce as well. And there are two things that I would like to highlight in this life cycle. One is the natal homing aspect of this. So turtles tend to nest where they themselves hatch. And what that means is that populations, in general, are genetically and demographically independent. So what does that mean? That means that stretches of coastline you don't have much mixing of populations, both that they're not mating, so you don't have sort of gene exchange, you don't have gene flow, and you also don't have much immigration into or out of the population. So the turtles in this stretch of beach belong to this particular stretch of beach, and the turtles of some other stretch of beach belong to a different group. And so that sort of each turtle region, each turtle sort of rookery, as you might call it, is sort of standing alone on its own. Additionally, you pair that with this fact that the little guys, their migration is strongly tied to ocean currents. So the reason this works is because they have these ocean current systems that carry them to nursery grounds. And I'm going to belabor this point a little bit. So what those two things lead to is that the ocean currents that facilitate the hatchling migration are the main drivers of population size. And what you see here is a graphic of, this is for the loggerheads, sea turtles that we just saw. So here's the main nesting area here. This white area shades sort of the maximum distance that hatchlings can move under the power of their residual energy from their yolk sacs. So they're born with little yolk sacs on their tummies, and they use that like a little battery to carry them offshore. And there is the places that are closest to the Gulf Stream, so that oceanic conduit that moves them to their nursery habitats. The places that are closest to the Gulf Stream are the places where nest densities, nests per kilometer, are highest. And that's what these graphs show. Different measures for different years, different regions. This is county level This is sort of region-wide across the southeastern U.S. This x-axis that you cannot see is the distance from the coast to the Gulf Stream system. So that the distance between this coast and this blue line here. And so the more turtles, so the closer that coastline is to the Gulf Stream, the more nests you have there. And that's because the more turtles get to the Gulf Stream, the more survive, and therefore the more will come back to nest later on in life. Here's another quick way of looking at, so this is the percent of the variation in nesting density along the southeastern U.S. that gets explained by the distance from the coast to the Gulf Stream. So you can explain more than 90% of the variation, the regional variation in differences in the number of nests per kilometer by how close it is to the Gulf Stream, how easy it is for those hatchlings to get to the Gulf Stream and get offshore and get to their nursery grounds. You see this is very important at regional levels, and even at the smaller scale, the county level. This is for Florida counties, where you might expect sand type, whether there's a lot of mangroves in the area, or whether there's a lot of beach development. Even at that county level, this is an important predictor for the number of nests, the nesting population size as a driver. And just to show you that this isn't unique to loggerheads, here's for the Kemp's Ridley. So more than 90% of Kemp's Ridley nests are deposited here near Rancho Nuevo. Are you all fairly familiar with the Kemp's Ridleys? And what you see here, this is a depiction of the ocean currents in this area. There's a westward Mexican current that comes sort of just south of the main nesting area. As it comes up against the continental shelf, it often creates this large eddy that would move turtles northwards and then out into the Gulf of Mexico into their oceanic nursery habitat. And what this graph shows is just the distance you would expect a turtle to travel if it was released at any of these locations along the continental shelf. And what you see is that centered right here around the main nesting site is the area which would promote the greatest amount of offshore movement. And so again, in the Kemp's Ridley, where you have the largest nesting populations are centered on these places where the hatchling migration is most favored. And so I'm belaboring this point to say that the oceanic stage of turtles is really important. And to the extent that they are capable of surviving is a huge driver in the overall population size. Now, that means that if you can understand that oceanic stage better, then you can have a better indication of the population trends, whether they are going to be increasing or decreasing, whether conditions out there have been good for turtles' survival, whether they've been bad, that sort of thing. Unfortunately, they're a very important stage, this oceanic stage, is what I hope I've convinced you of. But they're also a tricky one to study. They're small, they're out in the middle of the ocean, you can't see them by airplane. Most of the satellite tags that you would put on animals are way too big to attach to it, one of those guys, one of those gals. And so what do you do? So what I have been working on is modeling. So turning to modeling to understand their movements and distributions. And this is nothing new. People have been using ocean circulation models, rudimentary ones, since the 1960s to understand animal movements in the ocean. And they've become more sophisticated now. And so what we have are really nice products that show ocean current conditions at very fine resolution. So this is Global HICOM, the Global Hybrid Coordinate Ocean Model. They have ocean data spanning 80 south to 80 north at this 0.08 degree grid resolution. So that's about every 8 to 9 kilometers in the Gulf of Mexico. It's a little bit finer as you go further towards the poles. But you have these daily snapshots of ocean conditions at fairly fine resolution. We're looking at this is in the surface layer. And another cool thing about it is that there's this data assimilation. So it's not just predictions based on winds and conditions, but they're actually taking data from satellites, from instruments in the ocean and saying, here's what is actually happening, and we're going to refit those models to better account for actual conditions that occurred in the past to produce hindcasts. So instead of a forecast being a prediction, which are always wrong, you have a hindcast that's describing what happened in the past, which are often right. And so then you can take those velocity fields, so we have the surface of the ocean, and we can take software that allows you to put virtual particles in those velocity fields and see how they get pushed around by the ocean currents. And with this software, it's called Ichthyop, a really nice product developed by a friend in France. And you can simulate swimming behavior, you can simulate mortality and recruitment and growth and things like that. And so you can sort of treat these particles as virtual little animals. And this is a nice technique. The modeling approach can be very broadly applied for a variety of things. So for predicting spatial and temporal variation in turtle distributions. For instance, in this example, this is green turtle. Can you see those? These are white squares. These are major green turtle nesting beaches. And what we can do is we can release virtual particles at those nesting beaches in proportion to the size of the nesting group. And we can let them drift around for 5 years. And what this shows is that the distribution of those particles over a 5-year period that would say, if the animals are moving around in ocean currents, where would they likely accumulate? And the red areas are places where you would predict a lot of green turtles. Blue places are places you would predict very few, and white would be none. And then the green dots are coastal areas where there's some data on where the turtles are coming into the coastlines that we can compare our predictions to. And so what you can do is, for instance, estimate these contributions to mixed stock foraging areas. So that's mixed stock is just places where turtles from different populations might be mixing. And you can see how well your model does at predicting the proportion of turtles from each population at that location, and compare that to things like genetic estimates, where you take a genetic sample, you do some analyses to see what's the likely site of origin of that group of turtles, what proportion come from different areas. And this is useful for doing things like identifying research gaps. Where are there a lot of turtles, but there's not a lot of research? Maybe prioritize areas of conservation, where there are a lot of turtles and is a place of some management concern where you might be able to do something to keep turtles off of hooks or things like that. And it's also, in some ways, it's also really useful for providing context for in-water data. And I was just talking about the genetic analyses, right? And so the genetic analyses often, and certainly in the case of the green turtles, there are certain nesting populations that are known to be different from each other, but you can't resolve them genetically. And so the modeling allows you to say the likelihood that turtles in this area are actually from, say, Ascension Island versus Western Africa. And so you can sort of begin to build multiple lines of evidence to understand what's going on in the real world, what's going on with the turtles. And so this providing context for in-water data is something that's useful, in particular in data-limited situations, as was the case in the Deepwater Horizon oil spill from 2010. And so if we can apply this modeling technique to answer or address, at least, some questions related to potential impacts to this oceanic stage of turtles. Now, for a variety of reasons, it would be useful to know how many turtles were there and where they came from. And those reasons center on things where a damage assessment. What's the damage? Also, if you want to prioritize restoration, you need to know which populations of turtles you're going to try to restore. Who experienced that harm? How can you restore the Gulf based on who is in the area? And so what this shows is the predicted oceanic transport from the spill site. That's this panel. This is sort of the geographic, some geographic context of the spill. This yellow star is the site of the Deepwater Horizon oil rig. This blob here is what I am calling sort of the greatest possible extent of surface oil. So this is taken from the trajectory maps that NOAA produced. That they said this is that they had. Here's where we see oil, and here's the greatest extent that it might be. And so I said, all right, what's the greatest of all the greatest extents we had of those daily measures that they were providing? What's the greatest extent? So pretty big scope. This thin black line shows the extent of what's sort of generally characterized as the heaviest oiling. And then the orange shows the area of sea turtle rescue effort. And so what I did here is I released a bunch of virtual particles in this area of heaviest oiling. And I released those particles between April and August of 2010. And in this case, I ran the model in reverse. So I backtracked those particles to say, where was their site of origin? So if they're here, where did they come from? Don't step away from the microphone. Where did they come from to get where they are, to get to that location? And so to interpret this map, the red areas mean that this is a high probability, as if a turtle was in this area and was allowed to drift for 5 years, sort of a reasonable amount of time for their oceanic stage, if it would have a very high likelihood of ending up in that spill area at the time of the spill. Blue would be a much lower probability. This is log scaled, which that means, so the red is, the difference between, say, the red and the orange is a 10 times difference. So there's a 10 times less likelihood for the yellowy orange of going to the spill site than for something in red. And so this gives you an indication that the potential geographic scope is actually much larger than even the oil footprint itself. So we'd like to translate that. So that gives you a scope, but how do you translate that to numerical abundance? And I think it's pretty straightforward. So to do that, you want to know the turtles in an area of interest. So this isn't like oiled turtles. This isn't dead turtles. This is just how many turtles would be in that little black box that I showed you guys at that time. So that's our turtles in an area of interest. So we start with the number of nests at a nesting beach. We multiply that by the eggs per nest. So that gives us our starting population. So that's all the turtles that we could possibly have. And then we start carving them away. Not all of those turtles will survive to get to the water. So then we multiply that by the probability of hatchling survival. Then we multiply that by the probability of transport from the beach to the spill site within that time window. Not all of those turtles are going to survive that because you have things like tarpon eating them. So then we multiply that value by the probability of oceanic survival across a given year. And so then that in total gives you, in principle, the number of turtles in your area of interest. Because you can't go to the spill site if you've been eaten already, right? So that shouldn't count against BP. And so there's uncertainty in all of these measurements and all of these data. So we pulled them from the literature. The biggest amount of uncertainty is probably here. I just told you there's not much information known about the oceanic stage. And the estimates range widely from annual survival of 25% to 94%. With a median of about 81%. So we used all three of those values for computing purposes. So when you see error bars, that's what that is. So this shows our estimates. So the ocean current model predictions for green turtles, loggerheads, and Kemp's Ridley. And this black bar shows the damage assessment estimate from rescue survey extrapolation. So this is the survey in-water data. And what I find quite impressive is that that they're completely unrelated. I don't know anything about the turtles that they've seen. The model is an ocean model. It's just particles moving, right? And it does a really nice job of predicting, or is at least in close agreement with the number of green turtles that are estimated from in-water data, the number of loggerheads estimated from in-water data, and from I would love to say and from Kemp's-Ridley's as well, but that's actually quite a huge difference, an order of magnitude, right? So this is 200,000, this is maybe 6,000. So somebody's wrong. Somebody's wrong. We can't both say we're right. And being rather introspective, I question, perhaps I am wrong. So we'll look into that. And one of the things that I might be wrong about is turtles might not move like little particles in an ocean model. They might not just drift with ocean currents. And so I did some experiments with a terrific person, Kate Mansfield, a professor at the University of Central Florida, where we simultaneously track little oceanic stage turtles, and they're not tiny, right? But they're pretty little. They're still in the oceanic stage. And we simultaneously track turtles with these bird tags that she developed that are these tiny little 5-gram satellite tags that track the turtle position. We release the turtles with pairs of drifters and see, do the turtles go where the drifters go? And the short answer is no, turtles and drifters move differently. This shows the separation distance, so the amount that the drifters and the turtles separate through time. This is over a 2-week period. And so this is the time, this is the distance. And so we have pairs of drifters, so we know that we can calculate how far the drifters would move apart and compare that to how far the turtles move apart from the drifters. So here we see the drifters are moving apart, they might be actually, even 100 kilometers apart after, maybe not quite 100 kilometers, but let's say 100 kilometers apart after 2 weeks. The green turtles are closer to 500 kilometers away from the drifters in 2 weeks. And the Kemp's-Ridleys are, what is that? I can't read the scale. Maybe 200 kilometers apart. This graph shows our particles. So we release virtual particles at the same locations. And they follow it's a big mess of lines. They follow very nicely the drifters. So it's not that the particle model is wrong, it's just it's not what the turtles are doing. So we can look at, well, what are the turtles doing? We can take the ocean model data, we can subtract out the ocean current along the length of the tracks of the turtles, and that tells us what the turtle is doing. So you have track velocity, so track movement and ocean movement. If you subtract those from each other, that gives you what the turtle was trying to do. And we can talk about that later if you want. It's fun. But this gives you what the turtle is trying to do. So this shows you the orientation, the swim, not necessarily the movement of the turtle, because that's a combination of what the turtle is trying to do plus the ocean currents. This is just what the turtle was aiming for. And so it can see is, so this black line shows this orientation. So green turtles north of this black line tend to swim eastward. Green turtles south of this black line also tend to swim eastward. And so they're moving relatively quickly through the Gulf, the northern Gulf of Mexico. They're maintaining a straight course. And so any variation in their movement is not because they have variation in their swimming. They're doing the same thing. Any variation in their movement is going to be because of variability in the ocean currents. And so, even though the turtles are moving differently than the ocean currents, our ocean currents are still doing a good job of depicting that variability in transport, that variability in net movement, because that's what's driving the variation is the ocean currents, not the turtles. Does that make... we can talk about it later. In contrast, the Kemp's-Ridley does something quite different. North of this line, we see bimodal orientation. They go east and west, which is a great way to stay in the same place, right? You do that real quick, right? East, west, east, west, as opposed to east, 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 right? And so that's a good way to stay in this area. It's not north-south either, so you're staying along the continental shelf. So that's a good way to be retained in the northern Gulf of Mexico. In contrast, when they're south of that line, they go north. And that's a good way to get back to the northern Gulf of Mexico, right? So what you see is what I would term retentive and seeking behavior. So unlike the green turtles, who maybe don't care if they're in the Gulf of Mexico or not, they're just moving, the Kempsridley want to be there. So if we simulate that behavior in our models, and since it's a model we can compartmentalize and all this, so this shows if we include what we call just the retentive behavior. If a turtle's in that spot and it tries to stay there, boy, you get a lot more Kempsridleys. If you add in the retentive behavior, they want to try to stay there if they get taken there by ocean currents, and if they're not there, they're going to try to get there, you get an even higher amount. And you get estimates that come in much closer to the in-water data. Pretty fun stuff, I think. And what's nice about this modeling, so I just showed that, I think actually I'm going to gloss over this slide a little bit. So just giving the idea that you can do more with this modeling data. So it's I would say not entirely equivalent, but nearly so even to in-water data. But it also lets you compartmentalize and slice and look into details a little bit more. Give me a 1 or 2 minute warning too. Thanks. And you can say, if this is for the Kempsridleys, assuming retentive behavior, what percentage of different cohorts, so of those 200,000 turtles, what percentage are from the 2009, the 2008, the 2007 cohort, from these different nesting regions? You can see that this 2007 cohort was disproportionately affected. A lot higher percentage of their population was there. Not their population, of their year class was there, which might be especially problematic because those are the guys who should be, have undergone, they should be better at surviving because they're bigger, they're healthy, and so that, but we can use those sorts of things to inform our management and conservation plans. Additionally, we can add some geopolitical context to the impacts of these findings, and we can look at, this is for all turtles, so green loggerhead and Kemps, what is the number of turtles from different countries? And you can see, we have more than a dozen countries represented here. The United States over here actually is contributing, their populations are contributing less than 5% of turtles to that spill site. So if you're wanting to restore the Gulf, maybe you need to think beyond restoring U.S. populations and thinking about how to mitigate for these other populations that are using the Gulf. So to conclude, I want you to leave with the idea that the oceanic stage is a critical period for the sea turtle life cycle, and that simulations and ocean circulation models will allow you to understand that better, and that those simulations do compare favorably to in-water estimates, particularly when you have behavioral data to parameterize those models, and that the impacts to sea turtles of the oil spill extended well beyond the U.S. Modeling approach has a lot of potential, I think, to be used for further providing context to manage sea turtles and some other species too. So with that, I would take no questions, I suppose, but I appreciate your time.